So first thing we gotta do here is make a slope field, which is x plus y. I tried to figure out like what the easiest points would be to do first. So I figured when x and y are the same number, but they're negatives of each other, like 2 and -2, what's our slope going to be? 0. Yeah, so I did all those 0 slopes first. Then I did all the slopes where like x is 0, so the slope would be whatever y was. Then the slope where y was 0, so it would be whatever x was. Then I was able to find a pretty consistent pattern here of where x and y were 1 apart, but one was negative, one was positive. So like right here. So those slopes are all -1 right there. And then kind of similarly, like all these slopes were -2. And all of these slopes are a +1. And then the rest I just added together. It looks like I forgot one though. So it's 2. Remember, they don't need to be amazing, especially as the slopes get steeper. Like the difference between a slope of 4 and 5 and 6 is like, it's hard to do. So just make it look steep, and that's okay. Remember, what this represents is like a visualization of the derivative at every point. And so if we look at the derivative, like the slope of the tangent line, we can actually see what the shape of the curve itself would be. Basically, by looking at the derivative, we can kind of see the curve. There's a few different curves. The one that goes through 1, 1. So that's right here. Remember, what we want to do is basically just follow those slopes. Like it's getting pretty steep as we go in that direction. But as we come back this way, I see like I need to flatten out. And then I kind of just need to be guided by these points right there. So it's kind of this weird sort of open parabola thingy. Remember, they don't need to like trace, you don't need to trace over the lines, but they just need to be parallel to the lines that they're closest to. And then if we're going through -2, -1, that's right there. So that's like getting pretty steep down this way. It's too steep to even go significantly far to the right. Like I just can't get over enough. I'm just kind of stuck going downward. And pretty similarly going back this way. We're not going to see much of that curve, but we just kind of have to stick close to those slopes there. Remember, what these represent is they're called particular solutions. It's a specific curve that goes to a specific point whose derivative matches those values right there. So usually what we would think about this is like the plus c value is different, but as the derivatives get more complicated, like x plus y, I can't really think of what kind of function that would be that has a derivative of x plus y. That's really hard. That's really hard for me to visualize, unless I do a slope field, and now I can kind of see what it would look like. But other than that, I don't really have any idea. Like, so, yeah. We actually like won't be able to integrate that with what we're learning today anyway. So we don't really even know what the curve would be like. And it's been a long time since I've taken differential equations, so I really don't know how to integrate that. But so this is all I got. That's what the curves look like. That's what we're looking at. Okay. So now we're matching some slope fields. Some of these are easier than others. Do you guys see which one is 2x? Which number? No, yeah, number 6, yeah. So that's here. We can see that parabola shape. This one's easy to integrate. This is x squared plus c. You can just integrate it. And we did that one last time. Or you could say like, okay, I see the slope is 0 wherever x is 0. That's the only one that would apply. So similarly, if I'm looking for that one, do we see the one that has a slope of 0 wherever y is 0? Yeah, which one? Yeah. That's e to the x. Because that's a function where Actually, it's not e to the x plus c. It would be slightly different. It's actually a c e to the x. But anyways, it's a family of functions e to the x, like, because if the derivative equals the function, dy dx equals y. When we take the derivative of e to the x, it's just e to the x. So dy dx equals y. These other ones here are a little bit more difficult to think about. Which one does B go with? 5 or 7? 7? Why 7? What are you seeing on there?
A lot of the slopes are becoming kind of less as the numbers go. X and Y are closer together.
As the x and y closer together, slopes become less. Like, you're looking at like this group right there?
Yeah.
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 Where they're close together, but one's positive, one's negative.
Mm-hmm.
Yeah. Yep. What I noticed, yeah, that's like we want to figure out what's going on there. Oh, they're close together in number. We can see a slope actually of like 3 halves. Negative 3 halves to that part right there, that weird looking section. I was noticing that they got really steep as x and y became positive, whereas this one had some zeros as x and y became positive, which let me know that we were doing some subtracting in number 5, whereas we were adding in number 7. But yeah, these are just the kind of things we look for. So nothing too crazy. You'll never have to draw a slope field that's that many slopes. That's a lot. Actually, even this warm up here is like a high number of slopes to draw. Normally it'll look more like this. You'll have like 9 or 10, 12, I guess, to draw. Okay, so let's go to page 15. And we're going to learn how to solve these algebraically today. So, like we said last time, a differential equation is an equation that gives you information about the slope or derivative of some function family. And so the one, let me just scroll back real quick. The one that we looked at last time was dy dx equals 2x. That's the equation. It tells us about the derivative. We were able to come up with a slope field, and then we could find particular solutions by drawing them through the points like we just did. We're going to learn how to do calculus with these today. And I think I'm just going to jump into examples here. Let's actually go to page 17. We can see some examples first, and then we'll come back and talk about what these mean. So the method that we use here is separation of variables, or the phrase that we like to say a lot is separate and integrate. When we separate and integrate, they have to look like this. So it's some function of y times dy, some function of x times dx. And then we can just integrate both sides. So for example, in number 1 here, if I multiply both sides by dx and multiply both sides by y, I get y dy equals 2x dx. So notice there's just a function that's only y's multiplied by dy, and there's a function that's only x's multiplied by dx. Once we have separated the variables, here's the separate. Now we integrate. We just integrate both sides. So this would be 1/2 y squared plus c. This would be x squared plus c. But actually, we just write this. We don't do the plus c on that side. We just do it on the x side. The reason why is because if we're getting constants, unknown constants on both sides, we could just move it over to one side. So if I subtract c from both sides, what is c minus c?
0.
No, it's not 0. What is c minus c? It's not 0. C minus c is c. What is c plus c?
C.
C. What is c times c? C. C divided by c? C. Okay. This is because c, both of the c's, are unknown constants. One is 15 and the other is 12. One is 1/3, the other is 4,792. We have no idea what either of those c's are, and they're not a specific number. So when I do c minus c, it's not the same number c for both. It's two unknown constants. It's 10,000 minus 7. Okay, well the answer is just another constant that we don't know. So c minus c is c, c plus c is c, c times c is c, c divided by c is c. Especially because we're not given an initial point here, an initial value. So we just do it on the x side because we could move it over anyway. And so we don't really need to keep track of it. Oops, I took part of the y with it. That's weird. Okay, but we're not done yet. We have to solve for y. So we would multiply both sides by 2. And so we get y squared equals 2x squared plus what? Plus 2c? No, plus c. We don't know what c is. We're not given an initial value here. Then we square root both sides. So we get y equals plus or minus 2x squared plus c. In terms of the plus or minus, one of them could be right. It could be negative. It could be positive. We don't know. Because we have no initial condition. What we've just found right here is the general solution. This is an entire family of functions. And so we might need more information to figure out if it's plus or minus. But this is we're not being asked to find a specific solution here. We're being asked to find a general solution. Okay, let's look at number 2. A lot of times, here's how I see people solve number 2. They'll divide both sides by a dy. And so they're left as 1 over dx, y squared over dy. This will lose you all the points. Turn to your neighbor. Why? What's wrong with this? Okay, what's wrong with this? Have we ever integrated anything that looks like this before? No. Dx cannot go on the bottom. Dx has to be multiplied. So does dy. This is wrong. So they need to be in this form. G of y times dy, f of x times dx. We need both of those to be on top of both sides. The easy way here, we could just flip both sides, but what we should do in the beginning of this is multiply both sides by dx, divide both sides by y squared. So we get dy over y squared equals dx. Put a big red X by this one. Let's put it through there. Okay, integrate this one. Ready, set, go. Okay, when we integrate the left side, what do we get? When we integrate the left side, what do we get? Yeah.
Negative 1 over y.
Yep. What'd you use to do that?
Just the opposite of the power.
Yep. The reverse power rule. Yep. Exactly. Integral of the right side?
Hey, isn't it 1/2 y?
No. We increase the power by 1, so to be to -1, and then divide by the new power. Yeah. Integral of the right side? X plus c. We gotta have that plus c over there. Okay. When we're solving this, to get it, we always have to solve for y. I would just flip both sides of the equation, so y equals, and make it negative, like -1 over x plus c. Remember, like, you are allowed to do that. So x plus c is over 1. You can just flip both sides and make it negative. Yeah. So remember, like, this is our function family. This one I can actually kind of visualize pretty good what it would look like. This is our, like, rational function, and depending on what c is, we would have different vertical asymptotes. It's flipped, so if c was 0, it would look like this. If c was -1, it would be shifted over 1 to have a vertical asymptote at 1. If c was -2, it would be shifted over there to have an asymptote at -2. So it's like that family of functions. Okay, you guys do number 3. Separate and integrate. Okay, looks like you guys got the hang of this. Check in with your neighbor, just make sure you got the same thing. Okay. You guys got this first step, right? Separate. Sometimes you can decide, like, if you want to leave the 3 on that side, you can. Or you can bring it over. It doesn't matter. In this case, like, why would we want to bring it over? Like, we'll get the same answer if we do this. Why might it be nice to have the 3 on the left side?
Because it's an easier integral.
Yeah, it's an easier integral. Exactly. Yeah, we just get y cubed over here. Don't let this like dx in parentheses throw you off here. Like this is the same thing that we would see in an integral problem, right? Like if this was unit 3, oops. If this was unit 3 and we just saw that, we'd be totally fine with all that in parentheses with a dx on the end. So that's what we're doing here. We're just integrating both sides. So when we integrate x, what do we get? Mm-hmm. And we integrate sine x and we get cosine x or negative cosine x? Negative, yeah. I think about it like the derivative of cosine is negative sine plus c. Let me just cube root. Yeah. So that's the idea. Separate, integrate. Okay, what we're going to be given a lot is an initial value. In number 9 here, notice. Well, something's different about this. Turn to your neighbor. What do you notice that's different about this question here? Okay, so other than the fact that we're asking for a particular solution, that's obviously different. What else did you guys notice?
There are 2 variables.
Yeah, our 2 variables are different than what we were working with, right? We used to have dy dx. Now we have dx dt. This is probably like, particle motion, x representing position, t representing time. It's the same idea though. Whatever variable is on top, think of that as like your y coordinate. So x is our new y coordinate. That's why it says x of 0 equals 1. T is our independent variable. So that means we need everything with x on the left side, everything with t on the right side there. So we actually have x dx here already. We just need to divide by e to the negative t. And so that just becomes e to the t. And we multiply both sides by dt. Because it's 1 over e to the negative t. So then we're same deal here. We're going to separate and integrate. Or we separated. Now we're going to integrate. 1/2 x squared equals what do we get on the right side there? E to the t, right? Plus c. Now we just use this. So 0 is going to go in for what variable? T or x? T. This function is x of t. So we have to plug in 0 for t. And we should get 1 as our answer. 1, is that going to be this whole side, or does 1 go in for a variable? If x of 0 equals 1, what is that telling us? What's supposed to equal 1? This whole thing? X equals 1. Yep. This is saying t equals 0, x equals 1. I like to just solve for c when we first integrate here. I usually find it easier. So we have 1/2 times 1. What's e to the 0? 1. So 1 plus c. So what does c equal?
Negative 1/2.
-1/2, yeah. Okay, now I don't have just c anymore, I've got a specific number. So when I multiply both sides by 2 to solve, I do get x squared equals e to the t minus 1. Now we have to like do real math here. So we get x equals plus or minus e to the t minus 1. Turn to your neighbor, is it plus or minus, and why? Hold up, did I make a mistake somewhere?
Multiply the e to the t by 2.
Thank you, thank you, thank you, thank you.
Confused.
I was like, something ain't right. Okay. Yeah, math, right? Gotta do math. I'm gonna write this neater. 2e to the t minus 1. Okay, so should it be plus or minus or both? Plus. Why plus?
Because it says it should equal 1.
Yes. Exactly. So we're supposed to get positive 1 as our answer. So that has to just be positive. Notice like if this was equals -1, everything would still be the same except at the very end it would be negative right there. It wouldn't change our process of solving for c because that's 1/2 x squared. We'd be squaring -1, we would still get c equals -1/2. Everything would be the same. It's just that once we got to all the way to the end, we would have to know to put the negative sign there. So sometimes that's like a little twist with differential equations. We do have to think about our initial condition once we solve it all the way. You also have the option to, let me just do it over here maybe. You have the option to solve it first and then solve for c. So if I got x equals plus or minus 2e to the t plus c. At this stage right here, if I plug in my initial condition, I make that 1, which lets me know this has to be positive. I have 2e to the 0, so 2 plus c. And so I'd say, oh, c equals -1. And so my answer would still be the same thing. Is it okay that I got a different answer for c? Yeah, it's okay. I solved for it at different times. So c changed throughout. I still got the same final answer, which should be the positive version. I still got the same final answer. So depending on when you solve for c, c might be -1/2, it might be 1. It doesn't matter as long as you get to the right answer, and as long as as long as you get to the right equation at the end. You can have more than one answer for c. That's up to me as I'm grading it to make sure that the c's that you're getting match like the work that you're doing. Let's see. You guys do number 10. Ready, set, go. Okay, nice. You guys are good at integrating. On the right side here, what's our strategy for integrating that? What'd y'all do? 1 plus x all over x. What'd you guys do?
Do you integrate 1 over x plus x over x?
Yes. Hold on. Yes. Or 1 over x plus 1? Yep.
Yeah.
Exactly right. Okay, take 30 more seconds on that. So we gotta think about all of our integration techniques. We might have to do u substitution. Usually not though. Okay. When we integrate y, what do we get? When we integrate y, what do we get? 1/2 y squared. We integrate 1 over x, we get ln of x, and we integrate 1 and we get x. Yeah. Let's get 1/2 y squared natural log of x plus c. We solve for c. Did you guys get c equals 7? Then we solve, so we have to multiply everything by 2 and square root it. And we know to make it negative because we know that y of 1 equals -4. So we have to, that's something that we have to manually do. As we solve, we have to think about our initial condition. Okay. We're going to do a few more practice problems here. You guys are going to do page 16, numbers 3 and 4. In example 4, you don't need to do this part, but for part B, I'm going to add a little note here. So I want you to do this graphically and algebraically, calculusly, I don't know, algebraically. It's not really algebra, it's calculus. But what do we get on the left side when we integrate? Yeah. And on the right side we get 0.3t plus c. Okay, so if we solve for c right now, do you guys get c equals natural log of 10? Okay, and so our final answer here just becomes, how do we get p by itself? What do we have to do?
Moved over c and then divided p by 10 inside the natural log.
But if I want to get p by itself,
Do the exponential.
yes, yeah. So we could, did you do that afterwards? Yeah. We can just do it like right here if we want. So we get p equals e to the 0.3t plus natural log of 10. But there are different ways that we can write that answer. What did you get as your final answer?
10 times e to the 0.3x. I mean t.
Yeah. So this is a different final answer that we could get. There's actually a couple other ways that we could get that answer. One is if we use our exponent properties here and change addition in the exponent to multiplication between the bases, e to the natural log of 10 equals 10. And so we would get that. But actually, this is something that we'll see a lot in next class too. If I take this and solve it for p right now, we get p equals, before solving for c, we get this. And actually what this equals is this. How? Turn to your neighbor. How did I do that? This is before solving for C.
It's a constant, it could be anything, so. Just 'cause if you write it down, it's like-
Okay, Katie, could you explain what you did? Or why that works?
Is that right?
I think so. If I heard you right.
Because we're assuming C is a constant, we just don't know what it is. So it's the same thing that we did later on, just
Yes. Yeah, like it's this process there, but with an unknown constant. So we're able to split. Yeah. We're able to split this into this, and e to the c is still just c because we don't know what c is. So this is something we're going to see a lot next class. That's why I wanted to show it to you guys. I usually just do it this way. Like that was the answer that I got. That's kind of the normal way that I do it. But that way is really handy sometimes. If I solve for c right now, and I plug 0 in for t, and I'm supposed to get 10, I get c times e to the 0 power, which is just 1. So I see that c equals 10 in this case. And is that okay that I got c equals 10? It's a different c than I got before? Yeah, because it's in a different position. It's not the same c. This is an option that we have, and we're doing exponential growth and decay next class. So if you remember this from pre-calc maybe or algebra 2. Okay, but anyways, if you just did this like the first way that we did it, like, whoop, that's fine as well. Just wanted to show you guys this option. Okay, here's what I got for the slope field. So wherever x was 0, I put horizontal tangent lines. Wherever y equaled 1, I put horizontal tangent lines. And then I filled out the rest of the slope field there. Did you guys get this? Same slope field? Okay. Then graphically, if we're going through is the point 0,3. This is kind of a weird curve because we're flat here. Then we need to go up that way. But as we go this way, we kind of need to turn down, but then sort of flatten out again. Sort of a weird curve. When we separate the variables, what does our equation look like? What do we have on the left side? Ashlyn, what'd you get on the left side of your equation?
dy over 1y plus 1 dx.
You guys agree? I agree. Nice. When we integrate left side, what do we get?
Y minus 1.
Yeah. And right side we get? Yeah. Okay. So just so you know, we can do the same thing in this problem. We could exponentiate everything first and get y minus 1 equals ce to the 1/3 x cubed. Where we kind of combine two steps at once last time. This is what we're going to do next class. I'm going to get a different c here than if I solve for c here versus here, I'm going to get two different c's. I think one of them I'm going to get natural log of 2, and the other one I'm going to get 2, depending on when I did it. And then when we solve for y, it's just plus 1 on both sides. So my answers would either be y equals e to the 1/3 x cubed plus natural log of 2 minus 1, or y equals 2e to the 1/3 x cubed minus 1. This is what the graph looks like. Oops. So see how it has that like flat part and then goes up and then comes back down and then flattens out again. And notice here I actually graphed both solutions to make sure that they're the same thing, which they are. Oops. Okay. Questions on either of those? Okay. Nice. It's not too bad, not too difficult. Some of the delta math questions are a little challenging. There's a bunch of questions where you'll have to think about whether it should be plus or minus at the end of the problem. It might be a little complicated. You might want to do some stuff with e and moving the constant to make things a little easier. But it's good. It's good practice. You're basically guaranteed to see a question like this on the AP exam. Involving some sort of slow field and differential equation. This is actually a huge topic because it's so important later on as you progress in math. Like I said, there's a whole class about this, and it helps with differential equations. Help with springs. Like if you're trying to see like how much force you need to open up a big spring or compress a spring, is all like differential equations. Is what helps model that. So. If you're thinking about engineering, spring forward, as we say. That's for something else, though. Anyways, you guys can start working on the delta math right now. And yeah.